Good afternoon, everyone. My name is Wang from the ByteDance. So I'm happy to be here to represent our host networking team to present our work, a virtual switch platform by the vSwitch (BVS). We designed specifically for the cloud networking. Sorry. Yeah, just a little bit of recap component on the cloud networking, just in case someone is not very familiar with the cloud networking. So there was many different network functions in cloud networking. There's like, for example, security group, network echo, routing table, and there was a lot of other kind of like functions, which is like, for example, if you want to go to the internet, there's gonna be the internet gateway, or like a net gateway. There was like many different type of the load balancer, layer 4, layer 7, and some other kind of like things like a direct connect, VPN, blah blah, right? So all these functions actually is hosting on the different component. So some of them actually is basically is on the host side. We call it the compute node, right? Some of them actually is a centralized gateway. So if we zoom into the host side, there was a virtual switch actually running there. There was a bunch of functions there, but some of them maybe like cloud user not really able to see that. For example, there was a tenant isolation, and there was a VM location kind of things. But all these things like cloud user may not be really able to see this, but actually it does exist in the like a virtual switch when the cloud provider provided the cloud network function to the users. So next is we talk about a little bit on the virtual switch evolution at the ByteDance. So before we start our public cloud services, we actually have many years running our internal workload in our data center. There was a kind of like many different kind of like options we have done in like a virtual switch area. But when we started the public cloud services, actually we go over all the kind of like available options. Open source, or some of them basically from the other cloud provider that present their kind of like work. And we take the like OVS open vSwitch. I think this is one of the most popular virtual switch options there. So because of the time to market and the performance requirement, we take the OVS kernel plus offload options. So this is just give us pretty good performance in terms of the PPS, but because we take the offload options, there is a lot of kind of like restriction, especially from the hardware kind of like resources, because they have a very limited SRAM side, right? Which is the limited number of the sessions that we can offload and the functions we can offload. So there was a lot of other issues also kind of like popping up. For example, how if there was something goes wrong, how we can debug that, right? Because this is like the hardware. Hardware usually, if you debug something in hardware, usually is much harder compared to the software. And the connection per second, the CPS actually is pretty bad because we take the kernel version of the OVS. We have this kind of like a version running for roughly a year, and then we like because of those restrictions, we move to the OVS DBDK. So the OVS DBDK is purely kind of like a software version, right? And they give us a better kind of like development velocity. We can introduce new features in much faster manner, and they also kind of like much more flexible because the OVS DBDK is kind of like designed for the general purpose of the virtual switch and provide a pretty good debug abilities. But pretty soon we kind of like hit some kind of like other barriers. OVS DBDK is kind of like is a general purpose virtual switch. They probably provide literally maybe like 100 of virtual switch functions, right? But in cloud networking, we only probably using just maybe less than 10. So majority of the functions we actually not being used. And OVS actually over the years, evolution actually is pretty kind of like complex. And OVS is not designed for the cloud networking, right, at the very beginning. But of course, there was some cloud provider actually using the OVS, but it's a modified version. And we also take the same approach. But because of that, in cloud networking, usually like a security group is kind of like the mandatory features, right? So it's meaning like we have to enable the connect tracking. Connect tracking in OVS actually is a separate table, and because of that we hit some like performance bottlenecks. And the OVS is also not like a native VPC support. It's meaning like you have a lot of tables, but that table is not something like a routing table, security group table kind of things, right? Basically, it's a table number. You have to basically mapping that like table into something like you say, oh, this table is for the like routing table, for example, table 24, right? Something like that. I think it's when you start debugging, this kind of like it's kind of like a little bit hard because it's not associated with all the like VPC native kind of like concept together, right? There was mapping kind of this, and also like advanced VPC features actually is pretty hard to support. So that's why like we started kind of like build a Byte vSwitch, basically the VPC centric and the cloud scale and also high performance. We can also support continuous serviceability and the operational efficiency. So this is like the system architecture. We take the hierarchical architecture. Basically, it's the on the top we have the VPC control plane. Basically, it's kind of like expose all the APIs to the customer or to the EC2 control plane. And the BVS control plane basically is two kind of like major components. One is the BVS controller, which is like a north facing, interact with the VPC control plane. And we also have the BVS agent, which is the south facing, talk to the BVS data plane. So BVS data plane, basically, we take the separation of the slow path and fast path design. So we also using like the fixed pipeline optimized for cloud, user case compared to the OVS. So we also have the Byte flow forwarding framework. Basically, that's on top of the DBDK, but we have a lot of optimizations. So on the performance part of the system optimization, so I just highlighted like three parts. One is algorithm optimization. So DBDK actually, come with a lot of like algorithms, right? Some of them like you can choose. Some of them like they may just like come with the one kind of like algorithm. In terms of the LPM, like ACL, actually we are not using like a DBDK native algorithm because like those algorithms actually provide a really great lookup performance, but the trade-off that consume a lot of memory. So, but in our cloud scenario, I think scalability is one of the major kind of like objective, and the CPS actually is not the bottleneck of those kind of like even we go with some other algorithm which is like consume much less memory, but like the lookup performance actually is also pretty. I think is good enough for the kind of like a cloud kind of like user case. So so the other part is like hash table optimization, because in the cloud scenario, usually like you allocate multiple cores for the like DBDK PMD, right? So because like all these PMD threads, they actually try to access the single hash table. There was a contention there. But how to address this contention? Basically, if you just using that, like that basically will try to compute the the log, right? So that's why like we introduce a local cache. Basically, each PMD thread there was a local cache being assigned. And if there was a new session being created, remove their first like update the local cache, and then eventually update to the hash table. So we also introduced a hash, the hardware offloading framework, basically try to decouple the offloading policies from the underlying, hardware. On the performance part of the details, like you can look at the paper for the details. So in terms of the scalability, so the VM location basically is maintaining the mapping between the VPC and the infrastructure physical address space, right? So there was the challenges if we want to support the kind of like the VM location mapping in the cloud scenario. So one is like basically it's like a scale, right? The scale that we can like potentially manage up to 1 million of the VM locations within a VPC. Remember, this is just like within one VPC, right? Like in the region, we potentially can support like 10,000, like even more kind of like VPCs. You can basically simply imagine how many VM locations are gonna be in a single region. And the performance is another part. Basically, especially for this kind of like Kubernetes kind of like workload, right? Or the like fast kind of like workload. Basically, there was like a frequent creation and deletion of the VM and containers. So also like there was the VM location is dynamic. It's meaning like when you create the VM, this VM might be migrated to some other servers later, right? Or because of like hardware failure or some other kind of like maintenance requirements. So there was some quite a kind of like existing kind of like a method on the like pre-programmed model, on the gateway model, and the hybrid model. They all come with like their kind of like restrictions. So basically, we want to build like a one kind of like approach. Basically, is purely in data plane. It's meaning like we don't want any kind of like control plane get involved. So that we can support a really kind of like a high kind of programming speed and the the larger scale. Another like observation we are seeing basically is within the like one VPC, actually the percentage of the VM location entries being used actually is relatively small. So it's meaning like even like you have 1 million of the VPC, but at the it's not meaning like all the like 1 million kind of VM location table being used at the same time, right? And especially all these kind of like 1 million of the VM location table is spread across all the different like computer servers. So here is like a kind of like a diagram basically describe how this kind of like the OCA basically in data plane VM location learning kind of like process. So basically when the VM1 try to send a packet to the VM2 at the very beginning, he doesn't know where is the VM2 located. So basically the packet will send to the BVS1, BVS will send to the OCA gateway. So OCA gateway will do two things. One is forward the packet to the BVS2, and the other part is basically will send back a syncom message to the BVS1, which is containing the VM location of the information. So BVS1 will basically will program that into the local cache table, and the subsequent packet will be basically sent to BVS1 to the BVS2 directly without get the OCA gateway involved. So and we also support like periodically kind of like updating and the aging mechanism. So the other part is basically for the cost efficiency. So remember, we take the centralized cloud gateway kind of like functions, right? So in this case, for example, like this is for the service load balancer. Service load balancer basically is the gateway between the customer VPC pod and the infra pod to allow the customer access cloud infrastructure service. For example, DNS, NTP storage, etc. Because of this, the service load balancer is kind of like once our scale kind of like grow, we need to build a larger kind of like service load balancer, right? And there was a kind of like incur high cost and the performance bottleneck. So and we are thinking to see if we can bypass this service load balancer, but we want to like fully transparent to the cloud customers, and also we want to retain currently architecture that like integrity. So with that, we basically introduced the service load balancer bypass. So with that, we still send the first packet to the service load balancer. So but the service load balancer will kind of like carry the VIP and the vPort information inside of the IP options. So that basically information will send to the destination BVS. So BVS will basically keep that information, and when I send the packet back, then know what packet what the kind of like previously IP address needed to revert kind of like net back, right? So with that, kind of like the subsequent all the packet will be bypass the service load balancer. So with that, we can basically kind of like bypass the service load balancer. The traffic we will send from the BVS to BVS directly. So with that, we can just like provision a very small kind of like SRB cluster, and then we can make sure all the traffic take the the best optimal path from the BVS to BVS. So and the other part is like serviceability, right? Because like we built the BVS at the very beginning is we build this as a production service, right? Not something we just do it for the research purpose. So we need a approach to kind of like for us to continue to evolving our feature to do like a software upgrade to introduce new hardware, new platforms, right? Because like a cloud service actually is kind of like they are very sensitive on the outage. We need to figure out a way how we can do this kind of like continue the kind of like the service. So basically, we introduce the BVS headless upgrade. We take the dual process kind of like a method. So basically, we need to do the upgrade. We basically spin up another BVS process, and we sync up all these kind of like configuration rules from the SQLite database, and we also basically sync up all the previous sessions from the old process to the new process through the share memory. So then basically from the hardware NIC, and we can basically redirect the traffic to the new BVS kind of like process, and then we can basically kill the previous one. So with that, we are able to get the kind of like the upgrade kind of like downtime basically down to 22 milliseconds, even with like 255 kind of like the VMs. This is kind of like is a pretty large number. So with that, we can continue to do the kind of like software upgrade. If, as of today, like a BVS, when we do the BVS upgrade, we can do that during the daytime. We don't really need a kind of like reserve like middle night, and we do the BVS kind of like upgrade, because like 22 milliseconds actually is kind of like a majority of the customer workload actually is not aware of this kind of like outage. So the last one is basically operational efficiency, right? Because like hardware failure maintenance is always there, right? So we need to like figure out to see how we can do this migrate the customer workload from one compute node to another compute node. So the VM life migration basically this is like a mechanism already being there for many years, right? But how we can optimize that with the works better with the BBS. So mainly we introduce the two features. One is like session sync up. The other one is the relay forward. So maybe we can go through this kind of like a mechanism. So because like BVS is running on computer server, right, and they create all the flow sessions. If you just do the VM live migration, you just migrate the VM, you could kind of like state it from one computer server to another computer server. It's meaning all the BVS sessions is gonna be lost, right? So the the traffic basically landed on the new kind of like host will recreate all the sessions, which will cause a glitch. So with that, kind of like we can basically using a mechanism we call it the BVS session sync up. We can sync up sessions from the previously like the source host to the target host. So once the target host basically is VM migrated to the target host, all the like a BVS session already there. So the other optimization we have done is basically because like remember VM location is periodically update, right? If they like some other computer server is not update their VM location yet, they may still send the traffic to the previously kind of like the source host, right? So with that, we introduce a relay forward. So this guy will basically mark some entries, say okay, because this entry actually is migrated to the target host. If this BVS receive the packet, and then this BVS will forward the packet to the target host. So with that, if you look at the preferred number we evaluate in our production environment, so we can basically get this like a service downtime to kind of like within 300 milliseconds. Yeah. So in summary, so basically the BBS is a VPC-centric virtual switch platform we specifically designed for the cloud networking, and we discussed the performance optimization in our paper, and the VM location learning mechanism, and the service load balancer bypass, as well as software headless upgrade and the VM live migration. So BVS has been widely deployed at ByteDance for over 4 years. So if you get interested, you can kind of explore the ByteDance public cloud services at volcanoengine.com. Yeah, thank you. That's all I have. With that, I'm happy to take any questions.
Okay, thank you.